Hi guys, welcome to our channel of Sciences and Mathematics. Today's topic of discussion is going to be a topic under motion in two dimension, and that is a topic that we specifically refer to as projectile motion. Now we're going to see, among others, that this concept is very relevant to our day-to-day activities, like of course, the space technology, whereby some of the concepts are being applied in launching of rockets and satellites into space. So this is going to be very much essential. And of course, we're going to see other ways in which we can be able to exploit the concept that we have listed on the board, trying to solve problems related to the similar kind of motion. So without further ado, thank you and welcome. So as I've said, we're going to look at the sample question on the board, and this is going to give us in essence a summary of the concept of motion in two-dimensional space, and that is the concept of projectile motion. So in that respect, we're going to see how we can be able to describe different aspects of projectile motion using specific equations that maybe we are going to give in a summary form. So this is a topic for discussion. And as I've said, projectile motion is a motion in two-dimensional space. So I'm going to draw and give a small illustration, which we are going to use, of course, in trying to maybe describe some of the aspects and the questions that we have listed on the board. So in this case, I'm going to read the question through, and then I give an illustration, and therefore we'll commence and try to solve the specific problems that we have been given on the board. So a projectile is fired at an angle of 60 degrees to the horizontal with an initial velocity of 800 meters per second. Roman 1, find the time of flight of the projectile before it hits the ground. 2, the distance it travels before it hits the ground. 3, the time of flight for the projectile to reach the maximum height. And lastly, show that the shape of the flight is in form of a parabola y is equals bx plus cx squared, where b and c are constant. G has been given as 9.8 meters per second. So our illustration is going to have this motion in x and y direction being illustrated as such. So in trying to describe this motion, there's a distance that is covered from the point of origin to this one that we're going to denote using the letter R, and we're going to give the meaning for that. Now, so you can see this specific point, there's this maximum point that has been reached. So we're going to give this one as H, as the maximum height reached for that specific projectile. So when we were trying to talk about the concept of kinetics, we can be able to describe the velocity of this particular moving object using the tangent at that specific point. So if that tangent is moving at a specific angle, then we're going to give that one as angle theta. So therefore that is with respect to the y-axis. And then at a specific point, maybe can be able to illustrate still the velocity of that component of that specific object can be described using another angle. So we're going to give that one as angle theta. So we have two angles. The first one is giving the specific initial velocity, which we're going to denote by u, and then the second one is the final velocity at that specific point, which we can be able to denote as so that's the vector component of that velocity at that point v. So as I've said, the distance between this one and this one, suppose it's a stone that is thrown from this point of origin to another point, maybe m, then the distance between r and or m is referred to as r, and basically that stands for what we are going to refer to as range. And we're going to give a definition for that, perhaps using an equation. So we have also been asked to find the concept of a time of flight. This is the total time that the object takes to move from point 0 to m. So this is going to be given us using the initial m. And the h that I've denoted using the capital H at that specific point, this is going to refer to the maximum height that is reached by that specific projectile. And as I said, the u denotes initial velocity with which that projectile is moving, and then v represents the final velocity of that specific projectile. So we're going to use these different aspects and relationships in collaboration with what we have of course listed on the board to try and describe how we are going to find the specific components that we have been requested to find here, like the time of flight, or the distance it travels before it hits the ground, the time of flight for the projectile to reach the maximum height. So there's a relationship between these specific aspects that I've mentioned for that, and that show that the shape of the flight is in form of a parabola. So that one is we're going to talk about in mathematics and physics, maybe during the concept of graphing, but roughly we can talk about it here, since that specific motion that is being described by this object is in form of a parabola. So therefore, these are some of the ways in which we're going to describe it. So I'm going to do away with this so that we can go to the first, of course, our first challenge that we have mentioned there. Now that I've spoken in summary about what these different aspects of our projectile motion represent. So Roman 1 is find the time of flight of the projectile before it hits the ground. Now in this case, we're going to see that having this path of travel that of course we have referred to as, which is assuming the shape of a parabola. This one can be given in terms of an equation, as we said that from normal graphing, this is x is equals y. So therefore we can give this one in terms of this curve in terms of an equation, and this equation is going to represent that equation of motion of that specific object, and it's going to be given by, or described as y equals x, the tan of alpha minus a half gx squared over u squared, the cosine squared alpha. So this basically represents the general formula for describing the parabola or the travel path that we have indicated for that specific projectile. Now our first equation requires us to find the time of flight, and given this time of flight to be represented by t. So this one, of course, without going into the derivation of this specific formula for the sake of space, I just quote the formula. So this is given as 2u, where u is the initial velocity, the sine of alpha, this specific angle, divided by g. Now we have been given g as 9.8 meters per second. So basically here we're just going to do a substitution, and then we're going to find it's 2 times the u for us is a projectile is fired at 60 degrees to the horizontal with an initial velocity of 800 meters per second. So u for us is going to be 800 meters per second, and then we are going to see that the sine of alpha, the alpha that we have been told is the initial angle there is 60 degrees, so this is the sine of 60 degrees divided by 9.8 meters per second. So we have just left this one, the units, and then we are going to mention them. Of course, it's going to be given in terms of seconds, now that we have used that specific dimension for velocity. So therefore, this is going to be, so we'll do a calculation to confirm the same for that, 0.45. To do this decimal places, this is seconds. So therefore, the time of flight for our projectile, we're just going to do a substitution in this formula and find that it's 141.45 meters per second. It travels from point O to M. So this is the first one. So the second one, the distance it travels before it hits the ground. So the distance it travels before it hits the ground is represented by this specific letter that are given for range. So we have a formula also to describe the range for that projectile. So therefore, range is going to be described as the square of initial velocity, the sine of 2 alpha divided by g. So we're going to do a specific, or maybe a topic on derivation of all those specific formula. This is how we can be able to describe range given this specific illustration. So similarly, we're going to do a substitution for this. This is 800 squared times the sine of so for that case, our alpha is going to be twice that initial angle divided by g. So this is going to give us distance in terms of meters, because the dimensions that we have used for this is in terms of meters. So 6, 5, 8, 10, 4 meters. So this one can be converted to kilometers etc. So that's how we're going to find the distance it travels before it hits the ground from this point up to this point. And then the time of flight for the projectile to reach the maximum height. So the time it takes for the projectile to move from this particular point to this one, where it's h, peak for h, which is the maximum height. Of course, it's going to be given as a half the time of flight. So therefore, we say that time of flight is given as t, which is represented as 2u, the sine of alpha, over t. So this is going to be half the time of flight for it to reach the maximum height. So therefore, we had found that this t was 141.45 seconds. So therefore, we're going to divide this one by 2 in order to find the time of flight for the projectile to reach the maximum height. And this is going to give us 70.7 seconds. So that's to 1 decimal place. Therefore, that is going to represent the time of a flight for the projectile to reach the maximum height. And lastly, we are being asked to show that the shape of the flight is in form of a parabola. So, having said that we have a specific equation that is going to represent this travel path for this parabola, I'm going just to do away with this so that we can be able to have space to describe that. Now we said that y can be represented, or the function for that particular equation, or the equation for that parabola can be represented using y x, the tan of alpha minus a half dx squared over u squared, the cosine half alpha. So we are being requested to show that the shape of the flight is in form of a parabola. Now the general formula for the function for a parabola is bx plus cx squared, whereby b and c, these are constants. So therefore, for us to try and figure out how we can be able to describe this in terms of a parabola, from a trigonometric concept, we are going to see that, of course, I need again to just have a drawing of that so that we cannot be able to confuse ourselves somewhere. So I'm just going to have a small still illustration for that. H, this is R, this was U, initial velocity, angle alpha, and this was final velocity, angle theta. This was the Y, this is the X, and I hope we haven't forgotten. And so that was the shape of our parabola. So from trigonometry relationship, you can be able to describe X in terms of the U, the cosine of alpha t, and we can be able to describe Y in terms of U, the sine of alpha t minus a half gt squared. So you can see that from this we are having some kind of a relationship from the kinetics, of course, from the equations of motion, and then of course the trigonometric functions, but we're not going to see into detail about that. So in trying to show the function for this, of course, we can just try to use let's say this is the first and second equation, by trying to form to find a form of the first equation and trying to do a substitution for that one in the second equation. So in this case, we're going to make t the subject of our formula and do a substitution for us in the second equation. So that, therefore, from the concept of the x, you can be able to describe t as x all over the u cosine of alpha. Therefore, we do a substitution of this specific representation for t in the second equation. So therefore, it's going to give us y is equals u the sine of alpha into x over u the cosine over alpha. The whole of this minus I have g, and this is x over u the cosine over alpha squared. So in trying to, or maybe simplifying that one, we're going to find this one. This is basically going to form u cosine alpha over u the cosine of alpha, u the sine of alpha over u the cosine of alpha. And from the trigonometric ratios, we know that the sine over the cosine is going to give us tan. So therefore, we can write this one in form of y is equals x, the tan of alpha, minus a half g x squared over u squared, the cosine squared alpha. So this last part of the equation is going to give us a final form for the representation of this travel part for this projectile. So therefore, if you try to do a relationship or try to look at the relationship between that one and the equation of a parabola, which is given as y equals bx plus cx squared, the whole of this, for if we take that one as analogous to this, so this specific constant is going to be represented by the tan over alpha, and the constant for c is going to be represented by g over 2u squared cosine alpha squared. Of course, having seen that this section, other section of the equation is representing x squared. So that one basically, bearing in mind that this one having been a negative still forms a part of the equation that is analogous to the equation of a parabola. So therefore, the second component for c is going to be a negative, which is in negative g over 2u squared cosine squared alpha. So basically, that's how we can be able to show that that is the case for this particular problem, the set that we have on the board. So as we have seen this one, we have taken a summary form, but of course it has assisted us in one way or another in trying to describe different aspects of motion in 2 dimension, which basically entails the concept of projectile motion. So therefore, we're going to have a similar questions, but of course I've promised that we're going to have a derivation of these different aspects of the formula that we have quoted for finding this specific 4 set of problems that we've had on the board in one individual video that we're going to describe this one in details. So that is it for today, guys. Hope that we have understood different ways in which we can be able to represent range, time of flight, and maybe a maximum distance traveled or height with respect to motion in 2 dimension or maybe projectile motion. So that is it for today. Bye. God bless.